Andrew Dunning with news from Death Valley and Julian Gray discusses sand, science, and civilization. Welcome to the GSOC Geology Hour, our monthly gathering of geology enthusiasts brought to you by the Geological Society of the Oregon Country with support from the Beverly Vogt PSU Scholarship Fund and the Portland State Department of Geology.
Good morning, Alyssa.
Good morning. It's so good to see you.
Andrew, are you ready to tell us about news from Death Valley? And it's so good to see you.
Hey, everybody. I'm Andrew. I'm a recent master's student from PSU, Portland State. And I've been a fixture here for a few years now. And one of my personal interests and passions is in Death Valley National Park down in California, Nevada. It's probably the most geologically diverse national park in the country. It's the largest one in the lower 48, and I really like to go there. And I was just there a couple of weeks ago, and some of the things that have gone on there recently have been in national news. You may have heard of flooding and high winds and rumors of super blooms and all sorts of stuff. So I'm here to tell you a little bit about the things I saw and how things are down there in Death Valley. This picture that I'm starting it out with shows the temporary lake that is currently seated in the very bottom of Death Valley. I'll talk about a little bit more about that later, but this is from Dante's View is the name of this particular viewpoint you can drive to. And the vertical change here from where I'm standing to the salt flat where the lake is a little more than a mile vertical. So there's a huge amount of topographic relief here in this valley, and that's part of why the geology is so interesting. So to get there from where I live in Portland, it takes about 3 days. So I live in Portland, but I was going to meet my parents in Bend so we could all go down together. So Portland to Bend is the first leg. And then from Bend to Tonopah is the big 12-hour driving leg. We spent the first 4 hours in a blizzard from Bend to about Steens Mountain. The wind was insane. There were blizzards. There was dust storms blowing off of the Black Rock Desert and the Carson Sink and all of these valleys in Nevada kicking up dust. But Nevada is a beautiful and largely empty state. The Shoshone Range is right here, a great example of just some of the normal, average Nevada scenery as you're driving down through the middle of the state. We always spend the night in Tonopah because it's about 2 hours from the middle of Death Valley National Park. That's a wonderful mining camp, historic mining town with all sorts of these lovely old Westy style buildings and mining ruins. Very interesting place. It's sat at about 6,000 feet. So it's the second highest point on the drive between my house and Death Valley is this town called Tonopah. The other highest point is going over one of the mountain ranges at 7,400 feet. So Nevada is a deceptively high altitude state, and I think a lot of people don't know that. But then it's a 6,000 foot descent from Tonopah to the bottom of Death Valley, which is at sea level. Along the way, there's all sorts of cool things that are very close to the highway, such as the ghost town of Rhyolite, Nevada. This is one of a handful of large ruined buildings. You can see it right here as seen when the city was still a city in 1908. This town had about 20 years of good activity that was fueled by very rich nearby mines, but obviously those mines eventually ran out and closed, and now it's a very famous ghost town. We get to Death Valley, and it was the windiest I've ever seen it there. I've been in Death Valley in some very high winds. My highest wind speed I've ever seen was in Death Valley. That was gusts of 85 miles an hour. But this trip was much less gusty wind. This was continuous, sustained winds of 50 to 60 miles an hour. So it was a lot like walking to the door of the general store here at Stovepipe Wells. It was a lot like standing up in a convertible going down the interstate. It's a very strange, very annoying, but very cool to be in that sort of wind. We drove up just for fun to our usual camping site. We were staying at the hotel here because of the blizzards that we had to drive through and the general wind conditions. This is our normal camping site, so we drove up there to check it out. And this is what the view looked like from there. All of the horizon here is just wind-blown dust. And for comparison, this is what it usually looks like. So very limited visibility on this week in Death Valley. The high wind event also did something to this particular lake. And you can see that this is a lake, obviously, in the bottom of or nearby Death Valley. You can see the dust clouds blowing around. I just wanted to highlight how intense the wind was to have this kind of sustained wind. I've been in gusty wind where there's usually dips, but there were no dips in the wind here. It was like being in a wind tunnel the whole time we were there. But Death Valley is not really known for its lakes, but they do show up on satellite imagery. This is false color, so everything that is wet shows up as this bright blue color. I was standing right about here in that video, where this little lake is ponded up against the highway grade. But these two images show before the wind event and during the wind event. All of these lakes and bottom of these salt pans in the valley got blown northward. Like if you see here, this is in proper Death Valley. The bottom of the lake, the lake was blown about 2 miles to the north and flooded up all of these up to the secondary basin. And over here in Panamint Valley, where that video was shown, you can see this one down here gets blown north. So the wind was so insane that over the course of 2 days, all of these lakes blew miles to the north of their normal location. But this is what it normally looks like. Normally, there's no lakes in Death Valley. So why is there a whole bunch of water in the bottom of these desert salt flat valleys? And the answer was Hurricane Hillary. Back in the end of August of 2023, a post-tropical cyclone, Hurricane Hillary, came up from the South Pacific, slammed up against Mexico and San Diego, and plowed its way over the western U.S. Death Valley's right here where the star is. And on the 19th and 20th of August, it dropped 2.2 inches of rain on Death Valley in less than 24 hours. The previous all-time record for 24-hour precipitation was in 2022, and that was 1.7 inches of rain in 24 hours. So this just shattered that record and also dropped more than the annual average total of rain on the park. Huge amount of water. Death Valley National Park is the size of Connecticut. So basically they had 2.2 inches of rain drop all at once over an area the size of Connecticut, which then all rushed down toward the bottom of the valleys. That triggered major flash floods all across the park, which destroyed a huge number of roads and other park infrastructure. For instance, here you can see one of the major main washes flowing with flood water. This is after the flow level had come down a little bit. This is the primary highway in and out of this portion of the park, and it's currently under about a foot of water in this video. This is not normal weather for Death Valley, I would just like to point out. So some of the before and after pictures I just wanted to share because I think they're really impressive. This is the North Highway, which provides access to the northern half of the national park. Large sections of it, generally about 200 yards at a time, would get washed out. But this happened over a distance, repeatedly over a distance of about 70 miles. So they had to reconstruct large sections of this highway to get it back to usable condition, which took about 2 months for this highway. This road, this is Immigrant Canyon Road, just opened up about 2 weeks ago after 6 months of being closed. So damage like this is very common. Oh yeah, and it was also completely eroded away in many, many locations. And I really wanted to bring this up because a lot of the geology in Death Valley is very slow. You have very stable surfaces, limestones, and these mountains that have been stable for hundreds of thousands, if not maybe a million years. But when things do happen, they happen very fast. This 8 feet of erosion in this canyon happened in a matter of hours, for example. The most dramatic change anywhere in Death Valley from these floods was here at a tourist area called Salt Creek. This is a little tiny, highly saline desert stream with a population of little tiny pupfish about 2 inches long that live in this little river of water that's about twice as salty as the ocean. But it's sort of gone now. The entire riparian zone and all of the tourist facilities, including this really quite nice half-mile long boardwalk, is just gone. This is the main wash at the floor of Death Valley, and usually it doesn't flow ever because there's so much valley up above. When it does get water reaching the bottom of the valley, it'll sink in. It won't make it down. But there was so much water this time that it completely washed out this entire drainage, taking out all of the vegetation, all of the tourist infrastructure, and a huge amount of habitat for the fish populations is just gone, washed away. Very impressive. The fish are okay, by the way. There are other, not in this imagery, but a little further upstream, there's areas that were not completely eroded away.
I was going to ask about the pupfish, so I'm glad you addressed that. Very concerned about these fish.
They're doing okay. Excuse me. My favorite thing that happened is here in the sand dunes. That Stovepipe Wells General Store is a little off screen down this direction. So this is the primary sand dune area that people will come and visit and walk along. The flood plowed a channel through them. I've never heard of this happening before. I don't know if this has ever happened before in recorded history. So enough water sort of ponded up behind the sand dunes that it overflowed the sand dunes and carved a channel through them. These are not small sand dunes, so the amount of water that it must have taken to fill up and flow over and through them really is, I don't even know. It's very impressive. Just the change you can see here this is my favorite thing that happened. So back to the lakes. That's the thing that has really appeared in the news that you may have heard about most frequently, is the fact that there's currently a lake in the bottom of Death Valley. But that's not a new thing. Various times in the last 200,000 or so years, Death Valley has contained a lake. Sometimes it was a quite large and quite deep lake. This is called Lake Manly, named after one of the an old-time pioneer who got stranded in Death Valley and gave it its name. At times, this lake would have been about 600 feet deep, given current topography and ignoring any sedimentation or tectonic earthquake changes in the area. About 120 miles long, about 10 miles wide, very large lake. The biggest lake level, which is 90 meters above sea level, so that's a total depth of about 170 meters, because the bottom of Death Valley is 88 meters below sea level, 282 feet. This lasted until about 11,000 years ago. That's not even the biggest extent. So bigger lake than this, if you can imagine that. It's 165 meters above sea level. That's the one that sea level. That's the one that would have been over 600 feet deep. That was between about 135 and 186,000 years ago. There are all sorts of features around the edges of the valley at these different altitudes that reflect long-lived lake stands. These are called strand lines. This is an actual old beach bar, currently at an altitude of about, I'm forgetting. This is an altitude of 45 meters, is this thin white line. So it's 120 feet, ish, if my math is right, 130 feet. So these are 24 to 4. They're either 24,000 or 65,000 years old, depending on which analysis you prefer. These are very difficult features to get good ages for because the background erosion rate is basically zero, which is part of why these features are still visible 25,000 years later. So the last time there was a large permanent lake in Death Valley, it was about 2,000 years ago, and it was about 30 feet deep. And that's the lake that gave us the currently visible salt flats. It recently in August and again in February, when a major atmospheric river storm came through, this lake was refilled to a depth of about 4 feet. So nowhere near as deep as it was 2,000 years ago, but that's still a huge amount of water to fill up this lake in a matter of days. So it's about 4 feet deep when it was new. Obviously, it evaporates very quickly because this is the middle of the desert. It's an exceptionally dry climate there. But the last time this lake was this full was in 2005. So this is a once in every roughly 20-year occurrence to have this much water down there. And here's what it looked like from the shore. Again, the wind was such that the lake water was churned up into this sort of chocolate milk color and consistency. It was really quite strange. It was very, very muddy, this very brown sort of slurry. The salinity was about the maximum that water can sustain. So about 25% of the weight of this water was just dissolved salt. It was actually crystallizing along the bottom, sort of the lake bed, I guess. But the lake bed is also sitting on top of pre-existing rock salt and salt pan material. So you had rock salt hard pan, then you had about 4 inches of silty mud, and then about another inch of rock salt on top of that. That was new, fresh rock salt. And it was crystallizing just directly out of the water. It didn't need to evaporate first. It was just settling and growing out off of the muddy lake bottom. And that looks like this. You can see how all the salt crystals are sort of swept to the right because the wind was blowing to the right in this image. All the chop kicked up in the water back there gives you a really good idea of how the conditions were. And this left a lot of features that you actually see from the historic or prehistoric lake levels, like this beach. This is about 4 feet wide, about a foot tall. This reflects when the lake was completely full, 6 months ago-ish, after the hurricane. It's been smoothed out by people stepping on it, unfortunately, but it's exactly the same feature we saw that I showed in that satellite imagery, but on a much smaller scale. The rock salt chunks that were crystallizing had all these interesting little threads coming out of it. The water that was saturating the mud and the rock salt contains so much salt in it that as the water dries, evaporates out, it pulls out salt crystals that dry and crystallize. It's just like sort of capillary action like you get in a stalk of celery, but instead as it evaporates, it's pulling salt crystals out into these threads. Very delicate, very cool. And the entire ground was made of these very fine threads. Death Valley still contains a lake. The water level is getting really low. You may have seen pictures of people in kayaks going out onto the lake. But right as we were there, the water was getting just a bit too shallow for that. So this was more of a wading adventure for most people, including myself. This is the first time I've stuck my hands and feet into Lake Manly, and it's probably going to be a while before I'm able to do that again. So it was a fun and novel opportunity. Oops, that was a duplicate. And I wanted to bring this raven in just for fun. This is my last slide. We've been camping at this particular site. I showed this earlier for, I don't know, 17 years. This is our favorite place. We come here all the time. And every time we've been there, this raven, it's actually a pair of ravens, but in this picture, it's just this guy, has been coming there and visiting us the whole time we've been staying there. Ravens live a long time, so we have no doubt that this is the same raven. These are our old friends that come and visit us whenever we show up at this campsite. So that's all the news I have from Death Valley this time. Happy to answer any questions any of you might have.
Oh my gosh, Andrew, the salt crystals, amazing. That's that talk about feathery little crystals that are not going to last long.
Yeah.
So I'm not seeing any questions yet in the chat, and feel free, folks, to chime in into the chat. I do have, having been to Death Valley a number of times for geology field trips, winter and spring, one of the things that I recall, and I know you've talked about this in times past with your presentations on Death Valley, a lot of seems to me there's a lot of evidence of flash floods, erosion with all the fanglomerates, which is a type
Yes.
So it's not like this hasn't happened here before, but
Correct.
It's an opportunity for us to see erosion in process.
Yeah, and deposition. It's not super common that this happens on this scale. I mean, a lot of these washes flow every year, every time there's a slightly large rain event. Let me find one of these aerial images has yeah, so here that's not a great one. Okay, yeah. So in the difference between here, you can see that the bottom is all furrowed and channeled. And when you're there at the valley, a lot of these washes are either bright brown or bright gray, showing that this is new material that has been tumbled down. It's really cool to see where all the different washes flow and how they have moved around material. Interestingly, some studies have been done over the last 20 years or so. I learned about this at a conference last year, that the actual level of the floor of these washes doesn't change very much from storm to storm. Like you might think maybe a big storm would come through and wash everything out and drop the floor of the wash down, but that doesn't tend to happen, and it stays about the same, which is really interesting. Sort of a balance of material coming in versus going out.
Hey, Andrew.
Yeah.
I've got a question. This year has also been, this year has had a huge snowpack, especially later in this winter. And I'm wondering, does the melt from the snowpack to the west in the Sierras, will that reach the bottom of Death Valley and prolong the life of the lake?
No, it will not. Yeah, this is good. Let's see. So the Sierras are up in here. All of the melt on the east side of the Sierra either makes it to, most of it ends up in Owens Lake right here. And the last time water made it from Owens Lake to Death Valley was about 24,000 years ago. So to do that, it had to fill up Owens Valley, spill over into China Lake Valley, spill over into Searles Lake Valley, then spill around into Panamint Lake Valley, and then spill up over the Panamint Mountains and flow into Death Valley. Death Valley is, however, recharged from most of this area through groundwater and through the Amargosa River that comes out down this way up from, I think it starts up about here and flows all the way through here. But most of that doesn't really contribute to the current temporary lake in the salt flat, because the rate that water flows into Death Valley is just not as big as the rate that water evaporates. They get 2 inches of rain, but about 140 inches of evaporation equivalent per year.
Thanks, Al. Thanks, Andrew.
So we do have a couple questions in here. Bonnie Prang is curious. Andrew, we all know that you've been there a number of times. Did you see the lake in 2005? Were you there that year?
Not in 2005. I did see it in 2008, 2010. and 2015, but those were all much, much smaller than this was. We didn't go in 2005 because the park was closed for a long time, and also I was in about the 5th grade.
Oops. So some of us were a little older in 2005.
Yes.
So sorry, we have to remember that age factor there. Julian points out that this is a good reminder that water is the primary erosional force in deserts. That
Yes.
is true. Paul had a question. Where in Death Valley are good places to see fossils in the Tin Mountain Formation?
Well, all over the place. Anywhere there's limestones in Death Valley, which is most of it, there are fossils to be found. Even just on these alluvial surfaces. All of the rocks in this picture that aren't either white or brown, most of them have fossils in them.
Do you know like what kinds of ages those fossils tend to be, or is there?
There's everything from stromatolites to bony fishes to elsewhere in the park there are mastodons and much more recent large vertebrates.
That is wild.
There's 2 billion years of fossil history in Death Valley.
It's such an incredible place.
It is. So Ann Hudson has, as we're rolling up on Julian's talk here, Ann has a good question. Did you guys get to the racetrack? Because I know those huge rocks on the racetrack tend to move with wind and rain. Did you actually see evidence? Were you able to get close enough with the roads open?
The roads were open. We did not go there because we were the truck had our snow tires on, and that's a 45-mile washboarded road that is notorious for destroying tires. So we didn't go there this time. I've been there many, many times before, and I have seen those. I have actually been there while rocks were probably moving. You can't go out there because for the rocks to move, they have to be underwater, so you can't exactly walk out into the playa and see the rocks move. But yes, I have seen them freshly moved in the past.
Well, and that's what I'd recalled from some of your past presentations, but I was just kind of curious. And Kyle Dittmer saying, hey, that Death Valley was my very first geology field trip in 1980 as a new geology student. Thank you for the trip down memory lane.
Happy to.
That's hard to beat as a first trip. Sorry.
So Alyssa, I'll let you take the reins here.
Sure. Yeah, we're going to transition to the next part of our talk, which is going to be given by Julian Gray, who is our current president of GSOC. Is that correct?
Yes.
Yes. And I know this is one that people have really been looking forward to, a talk that people have been looking forward to. So from there, I will let you take the reins.
All right. Thanks, Alyssa. And thanks to Paul and the team for inviting me to share this talk with you. If you know me, you know that I'm a mineralogist and a hard rock geologist, and it may seem a little strange that I have maybe gone over to a dark side of sedimentary geology or something like that with sand. But I just want to point out that sand is really just tiny minerals. So I'm staying on theme, on brand with my interest there. So so this is not going to be a hard science talk. It is going to be a lot of eye candy, showing you different types of sand. And one of my goals is to maybe get you the next time you go to a beach or river, sand dune anywhere, to maybe take a closer look at the sand and look at the ingredients and maybe learn something about the environment that you're in. So let me go ahead and start my slides here. So the aims of my talk, it's going to be 2 parts. So my title was Science and Civilization. As I said already, it's going to be light on science. The civilization part really came out of a book that I read that I want to recommend to people, and we'll get to that in the last half of the talk. And it's not going to be some grandiose history of civilization, but really, sand is the basis of our civilization. It's really pretty amazing. It's the literal foundation of civilization. So we're going to talk first about what sand is, how it's classified, its components, and then look at some examples of sand And then we're going to talk about a sand crisis that's going on in the world right now and how that came about. So first of all, taking a purely geological perspective on what sand is, to geologists, sand is a grain size. It's just a size category for any sediment, any particle of minerals. And in particular, it is 2 millimeters to 1/16 of a millimeter. So these are right in the size range that's visible to the naked eye, most of the grains. With a hand lens, a 10 times hand lens, you can generally identify grains. And with a microscope, as I said, I love microscopes and optical mineralogy, so they are right in my wheelhouse for studying sand. They're already ground up. They're already at the perfect size to mount on a slide. Just briefly, where does sand come from? How is it created? Generally, the simplistic model, you've got mountains. Anytime a mountain range, anytime any rock is lifted up above sea level, it's subject to erosional forces. And, the freeze thaw, tectonic fracturing, joints, biological weathering. Plants will work their roots into joints, fractures in rocks, and break rocks into smaller rocks. Lichen attach themselves to rocks and they secrete enzymes that break rocks down. On the coast, pholad clams will actually grind rock up and leave holes in rocks and make sand in that way. So there's, just anytime anything is above sea level, it's being eroded, and many times at the shore, it's being eroded as well. Glaciers, of course, grind rock down, and gravity brings things down. Gravity and water and air move sand grains around into all kinds of environments, fluvial or lake and stream and river channels, into lakes, evaporite deposits, sand dunes, and of course beaches. And then offshore, you get reefs and coral islands. So all of that. So when you're looking at sand, of course, again, these are the things that sedimentary geologists torture students with, looking at the rounding of a grain. So when you're talking about purely detrital or fragmental rock, it's angular when it's first born. So when it's first chipped off of the rock or broken off of the rock, it's usually angular. But as it travels, so going from left to right in this slide, we're going from the source area where the sediment is first formed to where it's deposited and found. And at any stage along this, you can take a sample, a little snapshot of the geologic processes. So you get angular particles at the source. The grain size is generally larger, and something we call textural maturity, which is the mineral, you have different mineral components. Some of those components, for instance, micas and feldspars, they have cleavage. They're also susceptible to chemical weathering, and they'll break down. Things like quartz and are physically broken down, but they're more resistant, and they will last all the way to the beach in most cases. Zircon is eternal, and it lasts for billions of years. So you'll find that in beach sand as well. So you get a rounding of sand from where it's formed to where it's deposited. The grain size is reduced, and the number of minerals are sorted by water, by fluids, which are air and water. So just some of the geologic processes that are going on. In the field, I like to carry a sand chart to maybe describe these things in a field if I'm want to do that. But really, I mainly use that in the laboratory doing a size analysis or anything if I want to describe a sand sample. And this is the equipment that I use. They're sitting right by my left elbow here. I have these two microscopes. I have a stereo microscope on the left, It has a light source that hits the sample. It's reflected light, and that's just for a cursory examination and pick grains for further study. If I can mount it on a microscope slide and bring it over to the the petrographic microscope, which I like to refer to as a polarized light microscope. Maybe I'll spell that word correctly when I give this talk the next time. That microscope has all kinds of analytical equipment on it. It has polarizing filters and compensator plates and a rotating stage, so we can look at the sand grain and actually measure its optical properties, its refractive index, and other optical properties that allow us to identify the grains. And that's what I like to do. Sort of tied into the sorting here, and we had a biological component slip in, so sorry about that. We have the composition of sand. I divide it into light components and heavy components generally, and so you have those lighter components are things like quartz, mica, feldspar, which I call a quartzo-feldspathic quartz, which comes from quartz plus feldspar. But some of those more resistant components are things they are resistant, and many times they also have a higher density. And therefore, if a fluid is depositing something, these will get deposited first, and they may concentrate. And as, for instance, waves wash back and forth, as wind blows across the sand, it will remove some of those lighter components on the left and leave behind these heavier components. And these are very interesting minerals. They're interesting mineralogically, just from that perspective, but in science, these are very, very useful in prospecting. And there is one of my early jobs was with the U.S. Geological Survey. Andrew, you'll love this. Actually, my first job was in the Owl's Head Mountain with the U.S. Geological Survey, was in the Owl's Head Mountains, which is in the southwest corner of Death Valley, and we were sampling stream sediment. And then we were looking at the components and in different primary stream channels for potential indicators of ore deposits in this wilderness area. That area has since been turned into the China Lake Weapons, added onto the China Lake Weapons Reserve. So it's no longer open for access. I always like to recommend books, and these are two of my favorites. The one on the left, Heavy Minerals and Color, it's by British authors, and it's a great reference for all of these heavy minerals. Many of them are transparent, and you can use the petrographic microscope to identify them, and this is a great guide. It is way out of print, but you may be able to borrow one from a library. Rock-forming minerals on the right is used in just about every petrology class for identifying the common rock-forming minerals. And that book is actually, not only is it still in print, it's free online. You can download the whole book online. So that's available. Now, just before we start to look at sand samples, I like to break sand into a compositional classification based on its origin. Either it's the origin of the sand or where it's found, where it's deposited. So terragenic sand is terra, as in terraforming, or terra like land. So these are the things. Detrital, Lurs is a glacial, glacially blown silt. Glaciers themselves, moraine deposits, volcanic rocks. Biogenic, there can either be seashell fragments or fossils. That's another type. And anthropogenic, sand. We find glass. Bottled glass is a common component of beach sand. Slag, if you're in a stream channel near an industrial area, you'll find slag or metal particles. And near roads, you'll find metal particles as well. And then plastic is everywhere. And any plastic that is gets out of the waste stream and into the environment is broken down by microbes into microplastics that are then ingested by animals, and they start going back up the food chain and concentrated. So that's a major problem environmentally. Astrogenic is a word that some of the sand collectors are sand scientists are trying to push into the classification here, and I love it. These include microtectites, which are little bits of microscopic glass from impacts of asteroids or meteoroids with the Earth's surface. The kinetic energy melts sand and soil, throws up little droplets of molten sand or soil, and they freeze and fall to Earth, and they're scattered widely. Thousands of tons of meteorites, microscopic meteorites, fall to Earth every year, and they can be collected. You can find them. They're all around us, and they are just a few tenths of millimeters in diameter. So, okay, just want to throw this in: how we prospect, use sand to prospect. And if you follow, this is going downhill. If you follow from the bottom of the hill going uphill, and all of these dots are points where somebody has sampled sand, and all the black dots have, for instance, if you're looking for gold, they have no gold in them. And then suddenly you go up this stream drainage on the left going up the hill, you get a little bit of a the prospectors use a sniff of gold, and the channel on the right in that drainage is barren, and the one on the left has gold in it. And you continue to go upstream and you get back to barren samples. Then you've passed over the lode deposit represented by the orange fractures there. So this is the way sand can be used in prospecting. Some other ways that sand is used in science. Study was done by one of Paul Comar's students in the 1980s on sand from along the coast. And what she found was that sand, she looked at the rounding of the percentage of rounding of augite crystals in stream sediment. And so her hypothesis was that sand came out of the Columbia River and was distributed by longshore drifts southward along the coast. And as it did, her diagrams, there are each of those histograms. The left side of the histogram is very angular. The right side is very well rounded. And so what you can see is the histogram shifts from very angular going down the coast to very well rounded. So it's a very good story. One other part of the story, though, is that this transport up and down the coast was possible during the Pleistocene, when sea level was lower, and the Pleistocene shoreline was much further out to the west. On the map on the right, the green is current land, and the orange and red show the Pleistocene shoreline. And so this is shows that you're able to transport sand up and down the coast at that time. As the glaciers melted, sea level rose to its present levels. The shoreline encountered headlands, and that cut off circulation between some of these, they're called littoral cells up and down the coast. I just want to pause for a minute and just say one other thing. There is a hypothesis that this Pleistocene shoreline was more flat and a great avenue for travel. And so when the Bering Land Bridge was open, some of the Eurasian migrants may have moved down the shoreline, and that's called the kelp hypothesis for people distributing themselves in North America. So this just shows on the left between headlands, and I've heard the word pronounced littoral recently, but I learned it in the South as littoral. Littoral cells that and between these headlands we get longshore drift. The weather changes seasonally, and in the winter the wind blows from the southwest, and longshore drift is from south to north, and in the summer it changes from north to south, and this causes largely a buildup of heavy sands at the north end of these beaches, largely. One of the other things that's interesting, I'm still trying to grapple with this, is that you can go to the same spot at different times of year, and the beach will be covered with gravel, and the rockhounds are happy, and then come back another time of the year and the beach is covered with sand and the sand collectors are happy. Well, I do both, so I'm happy year round. But this is an interesting phenomenon, and something that I want to monitor, study, and learn more about. Just moving into collecting, there's also a collector's classification of sand. And like most collectors, people start out collecting something from everywhere, and generally as souvenirs of their visit to some place. Some people specialize in biogenic sands, fossil sands. I like garnet sands and green sands. I'll show you those in just a few seconds. And then movie sands, I'll talk about that. Famous locations and military sands. So what do these look like? Well, first of all, these are two very severely possessed sand collectors. The guy in the middle here in this picture has 150,000 sand samples. The couple in the foreground, that's their collection on both sides, and that's the first 1,500 samples in their collection on the right. So this can get out of hand. So what is a movie sand? Just giving you some examples of sub specializations. Movie sands are sands from beaches where a famous scene in a movie was filmed. For instance, Star Wars in part of Death Valley, and then the MASH television set, television show scene, and then the famous From Here to Eternity beach on Oahu. So those are things. Now, this is our first sand we're going to look at, and this has a lot of quartz and feldspar, and the very white particles are probably fragments of seashells, but you'll also see some dark spots in here. They're metallic spots. So what is this sand? Well, when you put it in context where it was collected, this is from the Omaha beach in Normandy, France, and those metal particles are actually bits of metal from military equipment that has weathered and become part of the sand. So this is a different part of that beach, and you have a large component of biogenic material in there. So I know there's one collector that I've met who this is his specialty, and he supplied these sands. I want to pause to talk about photographing sands. This is the setup that I use. It looks very weird, but I've cannibalized a petrographic microscope to fit under my stereo microscope. You don't get fine adjustments of the focus with a stereo microscope, and your vision, what's in focus is very fine. So I take multiple photographs, This is a mineral that I photographed, and I photographed it at different heights, and only one portion of the mineral was in focus in each of those slides. There's software that will process all of these images, take only the sharpest parts of the photo, and produce a single photo that is sharp and in focus. This is called focus stacking, and this is used. The entomologist first discovered it. The mineralogist, once they discovered it, have glommed onto it. And so when you're working with sand, this is what you get. You get a really sharp sand sample. And of course, a good sample is part of a good photograph, as well as good lighting. So we're going to zoom in on this. This sand is from Emerald Creek, Idaho. It's a garnet sand. It's mined for abrasive, but it's beautiful sand. We're going to keep zooming in on it, and we're going to go from reflected light to transmitted light. So these are at very high power. So you can see the structure on the surface of the crystal, as well as the inclusions inside. So. All right, we're going to blast through these sand samples to show you examples of sands, starting with biogenic sands. These are fossil sands from Hanahatchee Creek, which drains Cretaceous sediments in Georgia. There are a lot of fossils in there. You see teeth in there. There is a fish vertebra in the upper center part of the photo. And of course, teeth, and then rock fragments in there. One of the most sought after sands by collectors is this star sand from Okinawa. These are foraminifera, plankton. And so I have like to put things for scale. So there's a photograph of one of the stars on a penny for scale. These are seashell fragments. So the blue shells in here are mussel shells that are broken down by the surf. There are bits of gastropods, clams, and barnacles are a common thing. Barnacles and mussels are two very common components in the Oregon sand that I've seen. There's an amber colored grain just to the right of center in this photo. That's glass. That's bottle glass. And of course, there's ubiquitous quartz in this sand. So every sand sample is a mixture of many of the components I've listed earlier in my talk. This is another one. This beach had no name. It was near a boathouse in Charleston, so I just called it Boathouse Beach. And you see some beautiful shell fragments here. As well as rock fragment mix. And this is my transition to terrigenous material because 10 feet away, I collected this sample, which was detrital sand. And this is why I love the Oregon coast, because you can get 4 different kinds of sands on one beach. And you can get this, and then you can get garnet sands in another part of the beach. So we'll look at those.
Julian, this is
Yes.
Carrie. Just wanted to give you a quick time check. You are about 4 minutes from noon.
Yep.
Okay.
Working on wrapping. So oolitic sands, or oolites, oolitic sands, another highly mispronounced word in geology. Carol Miles from GSOC just gave me this sand a couple of weeks ago. This is from Iceland, mostly basalt. There's a famous sand from Hawaii and Southwest Hawaii that is 100% olivine. That's a friend of mine, Wade Mullen, who shared those photos. And it is like 90% olivine, a lot of magnetite, and some shells. Terrigenous sands back to Southwest Oregon, what I call quartzo-feldspathite rich sands. Garnet sands from Cape Arago. This is a beautiful sand. Here, lots and lots of garnets, and the same beach. There are 2 different kinds of garnets here, pink and orange, and then magnetite and in olivine and epidote and pyroxene in this. So this is Whales Head Beach near Brookings, almost all chromite and magnetite. And of course, in heavy sands, you sometimes find gold. This is from Alaska. This is from the Peter Iredale beach on the Clatsop Spit, which I'm trying to analyze all the grains to find the components here. So just show you that is an instatite grain, some quartz and feldspar, and of course plastic. This is not an Oregon beach, but this is another beach. These are plastic that is washed ashore. The civilization part is going to get shortchanged, but civilization is literally built on sand. Water and aggregate are the two most used natural resources on Earth, and everything is made from sand in some form, many of the things around us. And so, for instance, concrete, this is O'Hare International Airport. Whenever I fly, I see all that concrete, and I just think about all the sand that went into that concrete. We use 38,000 tons of aggregate for every mile of every lane of interstate. The average building contains 15,000 tons, and in your house, the average house, 400 tons of aggregate, which includes a lot of sand. If you need a visual reference, one cement truck holds 9 yards, which is about crudely 9 tons. So imagine how many dump trucks. We use 50 billion tons of sand every year. That's enough sand to cover California 1/4 of an inch thick. So that's each year. Why don't we just go to the deserts and dig up sand? It's everywhere, right? So sand dunes, you see this hundreds of miles because the sand is rounded. And if you build concrete or out of this, the sand grains will roll and it will not be structurally sound. You need the right kind of sand. It's also coated with an iron oxide, which chemically degrades. Many of our beaches, and I'm just telling you why we're running out of sand. Beaches, many of the beaches on the east coast of the United States are renourished periodically. About every 5 to 10 years, they have to be renourished. And we see stories all the time. So this is what a beach nourishment program looks like in North Carolina. You may have seen pictures of Palm Island. This is a crazy thing. This is the photo on the right shows you what each of those palm fronds looks like. It's a community. It's a village that they just built out, and they're bringing sand out of the sea adjacent to this area and destroying offshore habitats. Rhinelander Acres here, right 2 miles from my house. In fact, my house is in that view. This is a place where we manufacture computer chips, which are in everything. Glass is also a big use. The computer chips, this is the Unimem mine in Spruce Pine, North Carolina, where they mine a high quality silica, but not high enough for quality for silicon semiconductors. But they have to melt the silicon in something, so they make the crucibles that are used in the production of chips at this mine. And this is the only resource where they find that purity of quartz. And of course, hydraulic fracking. And I will end there and entertain any questions. So thank you very much.
Thank you, Julian. Everybody has just been totally fascinated with the sand and what you've been sharing. And I suspect you might get asked to do a full program on this because there's, I'm sure, a lot more that you could be sharing with us. So one of the questions that came up and is how, and this was related to the beach in Hawaii, how would olivine sand develop? How would you get it? Because that's kind of a rare mineral.
Well, In basalt, it's not that rare. And so if you saw in the slide, there were green, the cliffs behind the beach were green. And there's a flow that has a very high concentration of olivine in the lava itself. And so it's weathering right out of the cliffs onto the beach. And that's why there's a concentration there. If the source was further from there, the sand might get diluted and by other components. So it's really a proximity to the source, and it really occurs, and it occurs in a number of beaches around the world. There is another small green sand beach on Oahu. I have a sample from there, and then there are green sands from many beaches in volcanic environments around the world.
Oh my gosh. For purposes of time, we are a little bit after 12, and we can go ahead and take more questions, but we want to honor people's times, and definitely thank Andrew and Julian both for coming in today. That was just fantastic. So Julian, if you wouldn't mind stopping screen share, then we didn't get any other questions, and
I'm gonna Gary's gonna have to undo that. We found a technical issue. So,
okay, Gary, it's all on you.
There we go. Thank you. All right. Oh, okay.
Oh my gosh, as always, amazing talks. Alyssa, do you have anything that you wanted to ask or anything that you picked up on?
Actually, I did have a question. So, you mentioned the astrogenic sand, and I thought that was really interesting. H- I mean, it makes sense that we would have falls and especially things that were a lot smaller. But what would be the evidence that something you have is either a microtektite or a micrometeorite?
The first step let's take the microtektite first. They are round glass beads, so they'll look different. They may look different from everything else in the sample. And then at that point, if you can isolate it, then you have to go to analysis and get a chemical analysis of it. And sort of the same thing with micrometeorites. Interestingly, the micrometeorites fall within a very narrow size category. So the first thing that you do is look in that size category for something that's metallic.
Mm-hmm.
And then there are surface structures on it. So for instance, if you look at meteorites in thin section, you'll get droplets of olivine, and they have they're called barred olivines, and what they are is they have stripes of that high high interference colors that are typical of olivine, and so that expresses itself in a micrometeorite as lines on the surface of a bead. And sometimes there's also a little metallic bead on them, and I don't understand the genesis of the microtektites. They're also going to be magnetic. So the micrometeorite hunters have a procedure where they'll sweep, go and find flat roofs with lots of acreage. My dream is one day to go over there to Rhinelander Acres and sweep the Intel roof. It's a 1 million square foot building, so there's a lot of high probability of finding a micrometeorite there. They'll sweep it, then they'll wash it, and light stuff will float away. So they'll decant the light stuff, and then they'll screen it and then run it through a magnet, keep the magnetic fraction, and then it's just sitting there at the stereo microscope, for hours, sorting through every particle, looking for something suspicious. So, and then they mount them on a stub that goes into an electron microscope, and they do the analysis.
All right.
Fascinating.
So we do have a couple folks, Gary and Bonnie. Do you want to, Gary, take your question, and then Bonnie Campbell will come to you. You are muted.
Julian, Julian, you just partially answered a question that I had. And perhaps this is potentially subject matter for a future presentation. As a complete newbie to this field, it would be fascinating if you could share the life cycle of the analysis of a sample, and how you might take a cubic centimeter of sand and sort it, identify key components, what standard categorizations you use to separate it out,
Right.
and then what follow-up processes you use to drill deeper. And if that could be outlined in a flow, so that we could see where you were in your steps in your analysis, that I'd find that fascinating.
Yeah. Yeah, I can give a quick overview of that. And I wish I had access to the labs I had in the 80s with the U.S. Geological Survey. We would bring a sample back, sieve it. We actually used gold pans. That was the first step, was to use a gold pan and wash away the quartz and felspar and all those light minerals. We were only interested in the heavy fraction of the sample. And then when we got back to the lab, we'd sieve it and then put it in bromoform, which is a very deadly liquid, but it has a high specific gravity, 2.85. Felspar floats in this liquid, so you can skim off the top and keep the heavy stuff in the bottom. Then you run it through a very strong electromagnet at 3 different settings to pull the magnetite out, because you're not really interested in the magnetite. And then there's a paramagnetic fraction. So you get things like garnet and pyrite become magnetic at that very high magnification. And then there's a non-magnetic fraction, and that's the one that gets analyzed. So that's the actual flow. And I wish I had access to that kind of equipment. I'm left with just simply picking through grains with a pair of tweezers and separating them out and putting them on a microscope slide and analyzing them one by one. I also use an optical method called the spindle stage, where if minerals are 3-dimensional objects, and when you put them on a microscope slide, they're in 2 dimensions. The spindle stage, you stick the mineral on the end of a pin, and you're able to put it on the spindle, and you can rotate it in that axis and also this axis with the microscope, and you can get any orientation of the grain possible with that technique. That's a whole talk in itself. But that then you go to the optical mineralogy books and compare them. Optical mineralogy, you don't just sit down and measure the optical properties and bang, you identify it. It's really the epitome of the scientific method, because you have to ask questions. I think it's this mineral. You go to the tables and you say, well, if it's this mineral, it's going to show this property. And if it doesn't show that property, you've ruled it out. So you're ruling things out. So it is a powerful technique, but and a great intellectual exercise. So that's sort of crudely my flow, is just pick them by hand and analyze them with the petrographic microscope.
Well, bye, Anne and Bonnie. Do you still have a question? You've got your hand up there.
Yes. First of all, thank you and Andrew both for fascinating presentations. I will never look at sand again with I'll have a more discerning eye, if you will.
Success.
I am
All right.
I am going to be in Maui in November. My question is, as I'm running around collecting sand samples, is there a beach that I should not miss when I'm there?
On Maui. Well, there's the infamous road to Hana, and there's a black beach on Hana. I think there's also a green beach on on that road too. You might want to check regulations. Hawaii is getting a little picky about collecting sand, so be careful. Don't collect quart-sized bags. Just collect enough.
Yeah, right.
For your souvenir um, but those are the two places if you get that far. Otherwise, you'll find a lot of biological components, a lot of shells there, and they're very interesting shells, and they're in the middle of the Pacific Ocean, so they get different in a different climate, different latitudes, so they get different shells there. So yeah. Other than that, I don't know the island any better than that.
Well, thank you. And I will not take more than just, I have 35 millimeter old plastic cans that film
Yeah.
used to come in. I have a bunch of those, so
Yes.
I'll be discreet.
So my one and only trip to Hawaii was Maui, and found a cinder cone, and right next to that cinder cone was the prettiest bright red beach with really eroded cinder and scoria. And then right near there was a whole it had to be some sort of fossils, coral type of thing mixed up with the basalt, because it was a young basalt flow. So to me, it was a salt and pepper black beach, and then right next to the red beach. So I was happy. Volcanics. It was pretty cool. We did not get to the green beach. This has been absolutely wonderful. Gary, I don't know if are we still recording? Do we need to?
I never switched it off. Paul, protocol?
We've got so many great questions. I'm
Yes.
sort of looking at the attendance. I notice our attendance has been higher now that we have both Alyssa and Carrie as co-hosts. And that's probably no accident. I just want to thank Andrew again. There's a reason this event has been successful, and Andrew is a big part of that reason, because for 3 years he provided us such amazing content. And again today with your the Death Valley piece, that's one of the most popular of our videos that people watch. That and Clark Neuendorf's video about sand. So no, great job. We probably should turn off the recording, sort of let people know that, okay, if the show's over, you can go home. But we usually stay, and if Alyssa and Carrie, if you want to continue the conversation, we don't want to keep Andrew and Julian longer than they have to be here.